in our first unit, or day 8 in our first unit. We are looking at the sum, difference, product, and quotient of functions. So we're taking two functions and we're putting them together either by adding, subtracting, multiplying, or dividing. So any real number can be combined with these operations, and the same is true for functions. So let us have one function f be 3x plus 2. So this is a line with a slope of 3, an intercept of 2, and we are going to combine it with this function g of x that is a quadratic that's been shifted down 4. A reminder that these letters, f of x and g of x, they're just labels. We can use any letter that we want. So when we put these guys together, when we are adding these functions, we take function 1 plus function 2. And if we drop the brackets because we don't really need them in this case, and we put them together, this is going to give us x squared. I'm collecting like terms here, minus 2. This is our new function that is the sum of g and f of x. In the next example, we are minusing them, or taking the difference between the two. And this is going to give us negative x squared plus 3x plus 6. And if you're not sure how I did that, I distributed the negative here, and then I collected like terms. So this would be 3x plus 2 minus x squared. Two negatives make a plus 4. Collecting like terms gives me the final equation. We usually will write polynomials in this way, right? We always want to start with highest degree in the front and then go down by the degree. So this is degree 2, degree 1, and this is like having 6x to the power of 0. Power of 0 means it's a 1, so this is just a constant. So we always go from highest degree to lowest if possible. Now, if we are multiplying these together, then we have to distribute. Remember, from grade 10 or grade 9, we FOIL it out. So this is going to give us 3x cubed minus 12x plus 2x squared minus 8. And I don't have any terms to collect, so this is going to give me 3x cubed plus 2x squared minus 12x minus 8, if we write it in the correct order. And lastly, if we divide it, we should always check to see if there's anything we can do to factor either the top or the bottom, and to simplify it if possible. The top is already factored, 3x plus 2. There's nothing else I can do. The bottom, though, I have an x squared minus a 4, which is actually a 2 squared, right? So I have a difference of square in the denominator. So I could write this as 3x plus 2 over x plus 2 times x minus 2. If we remember our rules for factoring difference of squares. And if you don't remember how to do this, there is a video posted on how to do this. I'm not going to go over it right now because you can always go back and watch it. Looking at the top and bottom, there's nothing else I can factor out, so this is what it is. So you can just write it as is. This is the quotient. If it cannot be factored or canceled out or anything like that, simplified in any way, you could also leave it in the original state. That would be fine as well. X squared minus 4. However, there is something special when we talk about quotients. Quotients means we are dividing something, and one of the important rules in math is we can never divide by 0, right? That creates a black hole of doom. We do not want to divide by 0. So when we have a division, we always have to check the denominator and have the restriction that the denominator cannot be 0. So that means x squared minus 4 cannot equal 0, which means x squared cannot be 4, which means x cannot be positive or negative 2. Whoopsie. Positive or negative 2, right? Because if it's positive 2, 2 squared is 4, 4 minus 4 is 0. If it's negative 2 squared is, again, positive 4, 4 minus 4 is 0. So we have to think about restrictions when we do the quotient of two different functions. Okay, let's take a look here. A summary of what we just did. When we have two functions, for example, f and g, the resulting function we can write as f plus g of x, meaning we are adding the two functions together, but they both depend on x. And we just write them as is, as we did above, and simplify where we can. The important note here is that when we do the quotient, the denominator or the second function cannot equal 0. All right, let's take a look at some examples. It says compute each expression given the functions f, g, and h and k are defined as the following. So here we have 4 different functions. Notice that all the letters are different. We have an h and a k. That doesn't matter, right? We're just expressing that they are unique functions. So what is f plus g of x? Well, I'm going to take this one and add it to this one. So this is going to be 2x plus 1 plus x squared minus 2x plus 1. I'm going to combine terms. 2x minus 2x, oh, those cancel out, go to 0. And 1 makes 2, so this is just x squared plus 2 as my final answer. Next, I'm looking at f minus g. So 2x plus 1 minus, and instead of writing it in brackets and then distributing the negative, I'm just going to distribute it as I go. Minus x squared plus 2x minus 1. And now I'm going to collect like terms. 2x and 2x make 4x. Plus 1 and minus 1 cancel each other out. So I have negative x squared plus 4x. And you could even factor this if you wanted to. You could say negative x times x plus 4. Either way, it would be fine. All right, let's look at C. C is k times g divided by h, and look what's in the brackets now. Instead of it depending on x, they want us to put the 3 into the function. So our answer here should be an actual number. So let's set up the function first and simplify where we can. So k is 2 times g, which is this right here, and h is x cubed. So let's write 2x squared minus 4x plus 4 all over x to the power 3. And I'm not really going to go through here and bother with simplifying things. I'm just going to stick the 3 into the spots here. 3